This video is on Hashtable, its implementation, and the time complexity of its basic operations. Here's a roadmap of what we will cover. In this video, we will dive into one way to address the collision issues in storing data into a hash table, which is called open addressing, and we will use it to implement the basic hash table operations. After that, we will also cover the time complexity analysis of such basic operations. Just one word about collisions in case if you didn't learn about it. When you have some data pairs that need to be stored into a hash table, their key values will be fed to the hash function of the hash table to compute their positions or say the indexes in the hash table. Sometimes, two different pairs may end up with the same index. This is what we know as the collision issue. How does open addressing solve this problem? With open addressing, collisions are resolved by finding another open slot in the hash table. We call this process probing. It is handled via a probing function. Some common types of probings include linear probing, quadratic probing, and double hashing. Linear probing simply refers to the process of using a linear function to check if the next slot or the index is available. If not, keep moving to the next until it is available. Quadratic probing uses a quadratic function to identify the next available index. Double hashing uses a second hash function to identify the next available index. Let's use an example to explain how probing works. Think about this example. The hash function of this hash table is like this. It finds the digits corresponding to each character in the ASCII table, and adds them all up. After that, it divides the sum by the size of the hash table 11, so that the index can be retrieved. You have 4 pairs of data that you want to store into this hash table, like this, and you have already stored the first 3 pairs into the hash table. When it comes to the last pair, whose key is ant, and the value is 1000, you can't do it because it's supposed to have the same index as the first pair whose key is cat. When collisions like this happens, you can use a linear probing function like this to help you identify the next available position, so that you can store the pair ant 1000 into this hash table. So the probing function says when a collision happens, you need to recompute the index by adding a step number to the original index, and then divide it by 11, where 11 is the size of the hash table. Just in case if the next index is occupied, it will add 1 to the step number and recompute the index. It will do so recursively in case if the identified indexes are occupied. In our example like this, you will be able to get an index as 6 just by using the probing function for once. So index 6 is available in the hash table, so we can store the last pair of data into the hash table now, like this. The probing function that's used by the hash table is a linear function. It can certainly be replaced with a quadratic function or another hash function if needed. Now you know what open addressing is about and how it works. Let's move to the implementation of Hashtable. The implementation will be using this open addressing to handle collisions. Let's start with the Hashtable class definition. You will start by defining the size for the Hashtable class and declare 2 arrays of the same size, one array to represent the keys, while the other to represent the values. There would be 2 functions that are necessary for this class, the hash function and the probing function. However, we won't be defining them here. We will just fill them up with 3 dots as a placeholder. This is the starting point for the Hashtable implementation. Next, we will focus on implementing the 3 basic operations of hash tables, including the insert, search, and delete methods. We will start with the insert method. The purpose of this method is to add a paired data into the hash table, and it is where the collisions may happen and where collisions need to be handled properly. The insert method will take two parameters, one representing the key while the other representing the value. The two make a paired data instance. The first thing the insert method will do is to compute the index based on the hash function under the same class. Just in case the index is occupied, it takes advantage of a while loop to run the probing function until a next available position is found, then assigns it to the same index variable. So after the combination of the hash function and the while loop, it's guaranteed that the index represents a position where a new paired data can be inserted into. The last step, of course, is to add this paired data into the hash table. The key goes into the array representing keys, and the value goes into the array representing values. Both will be at the same index that's computed above. The implementation of the insert method only takes a few lines, but it also poses some challenges when it comes to searching for or deleting an element. Because when the element at the index computed by the hash function is not the same as the target, it doesn't necessarily mean the target is not in the hash table. In such a case, you will need to check other indexes computed using the probing function. Let's look at the search method next to see how we would handle such a challenge. The search function takes a single parameter representing the key value, and uses the key value to compute the index based on the hash function. After that, it checks the key at that index against the given key. If they don't match, then the function needs to check all the keys at the indexes computed using the probing function, and compare them to the given key. If one of them matches the given key, it will return true and stop the function from running. Otherwise, it will return false in the end. If you compare the search and the insert methods side by side, you are going to see that they share a lot of similarities because how open addressing works. In both functions, you need to run the hash function for once, and potentially run the probing functions for many times to compute the indexes you may need to check. Now, let's move to the delete method. The delete function takes a single parameter as the key value. It computes the index using the hash function for once, and it may use the probing function to compute more indexes to find if the given key has been stored in the hash table. If the given key is found to be at one of those indexes, the delete method will replace both of the key and the value with null in the two arrays representing keys and values, and it will return true in the end. Otherwise, the delete method will return false. With open addressing, the space in the data storage of the hash table is valuable. As more paired data are inserted, it will be a matter of time that you run out of space. To address this issue, the hash table implemented using open addressing typically has another method to help adjust the size of the data storage. This method takes no parameters and only aims to double the size of the hash table. As a result, it's named resize. As you can imagine, it involves a process of replacing the old data storage with a new one that doubles the size, and copying and pasting all the existing data points from the old storage to the new storage. This method is often called when the hash table is about to run out of spaces. Now, we covered the implementation of hash tables when open addressing is used to handle collisions. Let's talk about the time complexity of its different operations, starting from the insert method. The best case of the insert method is when the probing function doesn't need to run at all, which means that once the index is computed using the hash function, you would have an available spot to insert your data. In that case, It only takes a few steps to finish executing this method, which means that the time complexity will be constant time, expressed as big O of 1. What about the worst case? When the hash table is full, and there's not a single spot where you can insert any new data, in that case, this while loop will be in proportion to the size of the hash table. Because you need to run the while loop to figure out that every index computed by the probing function is not available until the index is out of the bound of the hash table size. That said, in the worst case, the time complexity is in proportion to the size of the hash table, which is big O of m. In case you forget, we used m here to represent the size of the hash table. What about the average case? We need the help from the expected number here to account for the randomness. In other words, we need to think clearly about what assumptions we have, what the random variable is, and what the corresponding probability is for the random variable. To simplify the average case analysis, we will approximate the time complexity to the expected number of probes, considering that they are in proportion to each other. We have only one assumption to cover. We would assume that the hash table size is m, and there are already n elements in the hash table. As you can imagine, n is a number that's always smaller than or equal to m. Here, we need to introduce a new term known as a load factor. It's denoted as alpha. The load factor alpha is calculated by dividing n by m, and it is a common tool that's being used to measure how full the hash table is. If you plot the load factor, you will see that it ranges between 0 and 1, and when the load factor is getting closer to 1, it means that the hash table is closer to being full. When it's close to 0, it means that the hash table has plenty of space for new elements to be inserted. The load factor alpha is also used to estimate the probability of successful probing of the insert method. By saying probing, I mean when you get your index via either the hash function or the probing function, and then check if that index is available for inserting data or not. The probability of an unsuccessful probing is the same as the load factor, alpha. The probability of a successful probing is 1 minus alpha. That's all about the assumptions. Let's get to the random variable and its corresponding probability. We will pick the random variable as the number of probes required to find an available spot. In other words, to find an available spot, we need to check for I indexes. I is an arbitrary number that ranges from 1 to n. What about its probability? For each probing, the chance of encountering another existing element in the hash table is the same as the load factor, alpha. If you find an available spot after probing for I times, that means there are I minus 1 times of unsuccessful probings. Based on the product rule of probability computation, you will need to multiply the probability of I minus 1 of unsuccessful probing and the one successful probing at I's time. So the probability of finding an available spot after I probes is simply 1 minus alpha, then multiplied by alpha powered to I minus 1. This part represents the final successful probing, while the remainder represents the I minus 1 times of unsuccessful probings. Now you have everything you need to compute the expected number of probings. The expected number of probings is computed in the same way as all expected numbers. It is a sum of items, and each item is a product between the random variable and its corresponding probability. We will relax the upper cap from m to infinitely large first, like this. After that, we will be able to estimate a part of the formula to a constant number based on infinite geometric series. Which part? This part. I mean the same formula, but without 1 minus alpha. Based on this, we can estimate the expected number of probings as a constant number, which computes as 1 divided by 1 minus alpha. It is worth noting that we see alpha as a constant number here when computing the expected number of probings, because alpha has nothing to do with the random variable I. However, based on what we learned from the load factor, we know that it changes dynamically as more elements are inserted into the hash table. As a result, we can conclude that the time complexity is in proportion to the load factor alpha, expressed as big O of 1 divided by 1 minus alpha. As for the search method, its time complexity analysis will be the same as that of the insert method. The major cost of the search method remains the same as the insert method, which is the computation of the index via the hash function and the probing function. I mean, this block of code. As a result, the best, worst, and the average case analysis of the search method are the same as the insert method. The same thing can be said for the delete method. Its time complexity analysis is the same as the insert method. Now you understand what open addressing is, how it's used to handle collisions, and the implementations of the basic operations of hash tables. In the next video, we will explore chaining, a different way to address collision, and how that will change the implementation of hash tables.